Hello everyone, welcome to the presentation on quality tools in the heavy machinery industry. And this is for EMGT 6120 Quality Systems at Ohio University for fall of 2015. This is presented by Team H, which includes Keith Ogg, Eric Delat, and Nick Kalmbach. So an outline of what we're going to go over today. First, we'll go over the objective of this presentation, the standards used in the mining industry, definition of quality related to the heavy machinery industry, a real-world quality issue, tools and methods used to solve this quality issue, and those tools include DMAIC, flowchart, fishbone diagram, RCA causal tree, and summary and conclusion. So the objective of this presentation. The goal of this presentation is to outline the quality tools used to solve the real-world quality issues in the heavy machinery industry. More specifically, the product we're going to be going over is in the mining industry, so a subset of the heavy machinery industry. We're going to discuss the standards used in this industry, define quality as it relates to this industry, examine the real-world quality issue related to an open-loop hydraulic pump, discuss how the quality tools used help determine the issue and provide potential solutions, and finally we'll summarize the tools used and the outcome they produce related to quality. So the standards used in the industry. MSHA is the OSHA equivalent for the mining industry, which is Mine Safety and Health Administration. And this outlines different areas of considerations like official emblem, filing, education and training, accidents, injuries, illnesses, metal and non-metal mine safety, uniform, regulations, on and on. The one I want to focus on is Section B, Testing, Evaluation, and Approval of Mining Products, since we're going to be talking about a specific mining product for our quality issue. And this section outlines safety standards of products used in a gassy or dusty environment like mining, special considerations on static electricity, electric motors, diesel engines, metal-to-metal contact, and fire-resistant hydraulic fluids. And the purpose of this section is to prevent safety issues resulting from fires and explosions due to the mining environment, which can contain, as I said before, gassy and dusty environments. Alright, a couple more standards used in the mining industry. As many of you are aware, ISO 9000 for quality management, and the subset of that, ISO 9001 quality management system, which basically talks about a process approach to managing quality, determine the needs of customers and incorporate that into the quality policy and objectives, and continuous improvement of the quality management system to really, in the end, better serve the customer's needs. And then also used in this industry is ISO 14000 environmental management, and the subset of that, ISO 14001, which outlines 17 elements to meet an environmental management system. And this also follows the Plan, Do, Check, Act cycle, which really entails planning an environmental policy and management system, implementing the environmental management system, and check and review that that environmental management system is effective, and then continuously improve that system to reduce your impact on the environment. So quality defined in the heavy machinery industry. quality in the heavy machinery industry is defined as how long a product will function properly when used in its appropriate and intended application. And a couple of the things I wanted to add to that, based on what I just talked about, is you need to include consideration of safe operation in regards to the mining environment, which entails gas and dust-filled environments prone to fires and explosions, which is from MSHA. The next point is efficient operation in regards to effects on environment. So continuously improving on the environmental effects of the equipment, and that comes from ISO 14000. And finally, continual improvement of products to meet and exceed the customer's needs, ISO 9000.
So the quality issue that we're going to be reviewing throughout this presentation is related to a situation that I'm currently dealing with at work, related to this open loop hydraulic pump that you can see here. I work for a company that designs and manufactures large drill rigs for open pit mining, and the function of this pump is to extend hydraulic cylinders which drive the drill bit and rod into the earth. So when this pump fails, you no longer have that functionality, you're no longer able to drill. So it's a pretty crucial component to our whole operation. Now these failures started showing up in different areas in the world, so a team was put together to try to determine why the failures were occurring and possible solutions to eliminate the failures. And in doing that, we were able to use different tools of quality to zero in on the root cause and propose potential fixes for this situation.
So the main quality tool that I want to go over first is DMAIC. DMAIC stands for Define, Measure, Analyze, Improve, and Control. Each of these steps can be used when dealing with a quality issue and will ultimately lead to an understanding and solution for a specific quality issue. Within DMAIC, many of the 7 quality tools can be applied to aid in the collection of data, organization of data, and determining possible root causes and solutions. So the nice thing about DMAIC is it gives you kind of a roadmap on how to attack the problem, but within each of those steps you can use some of the other quality tools that we've learned in the class. So going forward, the slides are going to outline each of the steps used in the DMAIC process and how they are related to the pump failure.
The first step in the DMAIC process is to define your problem. So in this case, our problem is related to the feed pump failures, which were leading to excessive rig downtime, and this was due to the loss of the drilling functionality. So the feed circuit functions were reported to not be performing, leading to investigation of the pump, which is where me and my team came in. The common sources of this feed pump are to run major components related to drilling, and like I stated earlier, when this pump fails, you lose all functionality. So our goal was to identify the causes of the feed pump failure and implement lasting solutions to the equipment. And through using the different tools of quality, we were able to accomplish that, or so we think. The second step in the DMAIC process is measure. So in this situation, we're trying to measure the extent of the implications of pump failure. And we were able to do that by looking at a lot of different documentation and data that we pulled from the sources listed here. So we're looking at different service orders, reports directly from the mine. We looked at the shift handover logs, basically when operators come in and leave. We look at the job cards, the timeline of events before and after the reporting, pump failure teardown reports, basically, which you can see in these pictures. After a pump fails, they send it off to be torn down and examined for possible causes, and you can see from these pictures that there are a handful of different issues. Figure 3 shows what's called a port plate, and there are these they look like pits basically, and that is caused by cavitation, and that was a key sign which led us to our final conclusion. We also looked at oil analysis, which is covered on the next slide, the component change history, OEM equipment manuals, hydraulic schematics, and then the OEM pump documentation. And by looking at all of this and kind of taking a step back and seeing it as a whole, we were able to measure basically the extent of the damage and help define that. Another example of measuring comes in the form of oil samples. So this is something that was conducted at the mine leading up to the failures. They basically took oil samples on different days, and then you can tell from the graph that the contamination level continually increases up until the 23rd, which is where they perform an oil change, and then your contaminants drop off back to what they started at. Now, doing this doesn't show that the contamination occurred on the 23rd. It just tells us that was one of their routine filter changes. And so if they were to continue this process, we would find that once the pump failure occurred, the contaminants would skyrocket, and they would clearly be able to see that there was a failure.
All right, as a part of the analysis portion of the DMAIC process, a flow chart was created to kind of assist in the problem solving and the root cause analysis of what the failures were, what the effects of those failures are, how they're observed, and a number of the other factors which are really leading to the shutdown of the mine. And what this picture or diagram is really showing is a chronology of events leading up to a number of problems, faults that were reported in electronic systems, and people's corrective actions which were taken at the time. And we're going to look at it a little bit more closely in the next slide. Okay, as you can see, it's the same diagram here with the red circle on it, and the red circle is really highlighting where we have identified a lot of the major problems could have been rectified. But again, the purpose of this flow chart is to help individuals involved with this project and evaluating this event or these circumstances, and really determining what the root cause is. And it allows a sequence of events, allows for chronological order, and it will also help facilitate, as we'll see later on in the presentation, actually in the next slide, complex decision diagrams or decision tree diagrams, where people have individuals or events lead to more than one option or outcome, or a sequence of events where kind of like in a programming language, if-else logics. If one thing, do this, else do something else. So it helps establish this order and these chronologies. And here in the events, the first fault was recorded at 1800. The individuals there at the site in real time are attempting to evaluate the problems, determine the causes of the faults, and take the necessary corrective actions, which is really beginning to get into how complex of a situation this really is, and especially when you're looking at it as an external observer and coming in fresh and new to a situation you may not be familiar in. But people are replacing fittings, there's a new faults, pumps are getting hot, and parts are being overheated. But again, as I had stated, metal debris is being found in the pump system. And maybe that's part of the original causes of what's going on. But here, circled in red, is kind of the larger sort of bullet that or bullet point or message to take home. What happened is that a number of fittings on the manifold were cracked, and in saying that, it's not that they were broken, they were just loosened, and it allowed air into a hydraulic system, and therefore the oil drained back into the tank. And when that had happened, now oil got into a system. As everyone knows, the gas pressurizes, but and it really stops the oil from pressurizing and now flowing through the system. And in order to correct that, proper bleeding procedures would have needed to have been followed, and for one reason or another, they were overlooked. So really, that starts to lead into why a lot of other issues that came along later. When you're talking about grinding and overheating and other factors, it created new problems, which sort of murkied the water and made things a little bit more complicated in actual root cause analysis. But as we had touched upon, the purpose of that flowchart really leads up into complex decision trees, and it even allows for people to take, again, a step back and say, well, what are all of the things that we're seeing? We have all these faults, we have all of these problems, and really it's hard to see the post-it notes, so they have been stated or stipulated on the left. Some of the problems that are being observed are suction valves. Maybe that's the root cause. Maybe they're closed. Maybe there's a kink in the drain hose. Maybe certain pumps have failed and shut off from overheating. But these fishbone trees are a very, very good tool at allowing large groups of people with a number of different backgrounds to get together and organize their thoughts and their perspectives and brainstorm and identify what problems may be causing some of the issues here in these drilling shutdowns, right? And then at that point, people can take a look at seeing, how can we verify that some of these electrical faults or oil temps really are real things that need, real problems that need further addressing. And furthermore, if they take a closer look and spend more time addressing those problems, are they really going to be identified as a legitimate root cause, as the source of all of the problems and all of the other faults and some of the things that are also issues, but not really the root cause? They're just critical issues that have arisen due to problem solving, and these types of diagrams allow for everyone to get organized and have a holistic perspective on the actual problem. Another tool is a root cause analysis causal tree. It's very similar and to the fishbone diagram tree, but this is, again, it goes back to why we did the flow chart first, why we do a fishbone diagram, because now we can sort of start using these if-else logics to have complex decision trees and other problem-solving methods for a number of reasons. But the problem, clearly can be stated. There's downtime due to a feed pump failure. Why? Is a very easy question, but to really answer that can be very complex. And these quality tools and these analysis protocols allow for people to get better answers than some of the simple ones, because they really are complex problems when you talk about oil pumps going down and open pit mining. So these causal diagrams are really a result of a much higher level of understanding of chronology of order, chronology of processes, and really having a very good understanding of what the corrective actions should be at each stage, and how you can rule out whether or not some of the other side effects of an illness or an ailment or a failure, other subsystem failures, are or are not really the root cause, or whether or not they're secondary effects due to an alternate primary failure. So these kinds of tools can be very helpful in people evaluating information and making well-informed decisions. Okay, due to time constraints, we're gonna kind of sort of skip over and quickly go over some of the other steps. But the DMAIC process itself is a very important process, and really what we'd like to do is talk about why some of these quality tools, such as DMAIC and causal trees and these other tools, why are they so important? Because of the cost of quality. Think about the costs of broken pumps or metal in other subsystems, or even ultimately the mine and the pump the mine shutting down and ceasing to produce any raw materials because of a simple pump failure. Well, there's a lot of cost of quality associated with that, and in talking about how can we address these root causes, that's something we'll get a little bit more into, but in principle there's a lot of different ways to go about doing that. You can design in safety measures, redundancies. You can do additional training to personnel. You can have training sessions and seminars, and you can also look at human factors engineering and sort of do real-world walkthroughs to interact with the situation or the equipment as it's being used in the real world, as opposed to in an engineering lab or in a simulation. Those things, the simulations are good, and lab work is good for designing and prototyping, but until you actually have a fully functional system and can go experience it and see how people would use it on a daily basis in the real world, you may not, until you do that, you may not have a good understanding of unexpected failures or limitations or constraints that may arise in day-to-day use. So cost of quality is a very important concept, and which is why it's very important that people have a good working knowledge of some of these quality tools, such as the DMAIC process, as well as others. In this slide, I'd like to talk a little bit about implementing quality throughout in an organization. Quality is such an important concept, and far too often it is believed that quality is the sole responsibility of the quality department, when in reality it should be the responsibility of everyone involved in the organization, be it engineers, mechanical engineers, or design engineers, or even technicians or guys working on the mine at the mine and at the job site. So quality really affects everyone throughout the organization. The cost of quality can be high, and the process of looking at all the faults, all the failures, and all the problems which are occurring during any given problem, and really taking an in-depth look at evaluating what the root cause of that is, a very laborious, very time-consuming, very costly activity for an organization, because those individuals and those resources could have been perhaps spent in another way rather than fighting fires or troubleshooting or doing root cause analysis. Perhaps those resources could have been used in a more beneficial way. But with that being said, the implementation of quality management tools and quality management systems is a critical and vital concept for any organization, and it helps them continue to have sustainability and improved efficiencies. The better the management practices are of implementing these quality tools, the more successful an organization will be at driving towards continuous improvements throughout all aspects of their organization. Observing all the different failures and faults which were occurring during this incident, looking at the defects or metal shavings and all the other problems that were occurring, and then determining which failure was really the true root cause, is just one small aspect. But using these management tools like matrix diagrams and activity network diagrams and flow charts are critical, because that's how this problem got solved. And so yes, there's a tremendous benefit for that. But taking a step back and looking at lessons learned, and communicating those lessons throughout an organization and using quality management systems to do that is very important, and really benefits the organization much more thoroughly and over a longer lasting, wider ranging period or portion, or just in general. It just affects, has a much larger impact on the actual performance of that organization than simply getting to one isolated problem, or solving one isolated problem, or one isolated incident. And so, again, there's a lot of other things you can do. Failure mode and effect analysis is some of the tools we could have used. We could design for Six Sigma in the future. We can look at human factors engineering, or human error and human error in use. And we can look at a lot of gauge R&R and reliability. How much air was too much when it got into the hydraulic oil? Can we filter out metal shavings? So there's a lot of problem solving that went into this. There's a lot of lessons learned. There's a tremendous amount of things that can be communicated throughout an organization to continue to drive continuous improvement and improve quality and reliability and performance throughout not only open pit mining, but throughout the whole organization. And using quality management, a good quality management system will be very helpful, not only in this specific situation, but in many other situations which may arise in the future. Some more similar than others, and some perhaps hopefully less serious and significant as this one.
So to sum things up, the quality issue we've been looking at was related to the pump failures, which led to extended downtime of the rigs. The failures led to investigation, including myself and a team of others located in different areas of the world. We used the DMAIC process, flow charts, fishbone diagrams, and an RCA causal tree to help us determine the root cause of the failures and come up with potential solutions to remedy the issue. So after a lot of effort from a handful of different individuals around the world, we were able to propose a solution to prevent the feed pump failures. So it was concluded that the failures were caused due to failure to bleed the pumps properly, which trapped air in the system and resulted in cavitation. So our solution that I have, it's actually in the process of being implemented right now, but we are adding process sheets to our internal manufacturing process so that the pumps will be in working condition as before they leave our facility. We're also going to implement the same type of process sheet to send out to the field, and that'll be included in our operations manuals. And it basically talks about the proper way to bleed these pumps out. We're also adding an additional hose to a specific port on the pump, which will help bleed out the air. So what we found is that operators simply weren't doing this step. So by adding a hose to this port, it will automatically bleed the pump with no need for anybody to take any additional steps. Also, we plan on adding a high pressure filter downstream from the pump, because when these pumps fail, it's catastrophic and it sends tons of brass into the system. So by adding this filter here at the outlet of the pump, we will trap all of that contaminant and prevent it from flowing through the rest of the hydraulic system, which ruins downstream components. So based on all the different tools that we used, this is what we came up with, and it will be implemented within the next month, and then we will find out if it worked, and probably another 2 or 3 months after that. So at this time, we don't have a conclusion to determine whether or not what we have done is going to work, but those were the steps that have been taken. I'd like to invite all of you to post any questions you have to the discussion board that this